All right. So, you sent in some research on this new mode thing,
Uh-huh.
and it looks like it's trying to solve a
Yeah.
pretty fundamental problem
Yeah.
in how we're building these language models.
That's right. It's all about taking universal transformers,
Right.
which are incredibly powerful at learning
Yeah.
and making them actually usable at scale.
Right.
Because right now they're just too computationally expensive.
Okay. So for those of us who haven't been like living and breathing universal transformers,
Sure.
can you remind me what makes them so resource intensive?
It comes down.
Oh, hey there. How can we help?
Can we go through the abstract and the introduction part first?
Absolutely.
That's a great idea.
Let's start at the beginning.
Okay.
So the paper introduces MoEUT
Uh-huh.
as a way to make universal transformers more efficient.
Right.
The key problem they're tackling is the parameter compute ratio.
Okay.
Universal transformers share parameters across layers, right?
Yeah.
Which is great for learning complex stuff,
Okay.
but it makes them computationally expensive.
Right.
So Mo uses a mixture of experts approach
Yeah.
and two novel techniques to fix this.
Layer grouping and peri-layer norm.
Exactly.
Okay, so now that we've hit the high notes,
Yeah.
do you want to jump into the resource intensity thing?
Sure.
It comes down to how they learn.
Yeah.
Universal transformers use the same parameters across the layers.
Okay. Oh, yeah, uh-huh.
Can you remind me about the universal transformers?
Sure thing.
Absolutely.
So universal transformers,
Yeah.
dot creature, are a type of neural network architecture.
Exactly.
They're like regular transformers,
Right.
but with a twist.
And that twist is pretty important.
They share parameters across layers.
Uh-huh.
This gives them a recurrence in depth.
Right, which is what we mentioned.
And that allows them to learn complex patterns,
Exactly.
like understanding language better.
You got it.
They can decompose structured problems,
Yeah.
generalize to longer sequences.
Mm-hmm.
But this parameter sharing
Yes.
is what makes them resource intensive.
That's right.
That's what MoEUT is trying to fix.
Precisely.
And it's all about efficiency.
Okay, so now that we're all on the same page,
Yeah,
do you want to jump into the resource intensity thing?
sounds good.
It comes down to how they learn.
Yeah.
Universal transformers use the same parameters
Okay.
across all the layers of the model.
That's what gives them the recurrence in depth
Uh-huh.
that lets them learn complex patterns.
Right.
But it also means that every layer needs to be processed.
Yeah.
So it's like having this amazing multi-talented team,
Exactly.
but they all have to weigh in on every decision,
Yeah.
no matter how small.
Exactly.
And that's where MoEUT comes in. It's taking this team and making it way more efficient
Right.
by introducing specialization.
Specialization, like how?
Well, they're using this idea called mixture of experts,
Okay.
which is basically having different experts,
Right.
each trained on a specific type of task.
Okay.
And MoEUT applies this to both the processing and attention.
Wait, so instead of every layer working on every piece,
Right.
MoEUT is saying, okay, this expert is really good. So let's have them focus on that.
Precisely.
They use something called SMO to score the experts
Okay.
based on their relevance to the specific data.
Right.
Only the top performing experts get activated for each task.
Okay.
This Mo is like a ranking system,
Yes.
picking the MVPs for each play.
That's a great way to put it.
Yeah.
But wouldn't that lead to some experts getting all the attention
Yeah.
while others are left on the bench?
Right.
How do they make sure the model learns evenly?
That's where regularization comes in. Think of it as the coach making sure everyone plays.
I like that analogy.
Yeah.
But what about the attention layers?
Yeah.
Aren't those critical for understanding relationships?
You're absolutely right. Attention is crucial.
Yeah.
And Mo tackles that with Switchhead.
Okay, switch out.
It works in a similar way to SMO,
Mhm.
but instead of selecting experts for the whole network,
Right.
it dynamically chooses value and output projections
Okay.
based on the incoming data.
So it's fine-tuning the focus of the model on the fly.
That's exactly right.
It sounds like they're optimizing every single aspect.
They are, and it doesn't stop there.
Oh, there's more.
They've also introduced this idea of layer grouping,
Layer grouping.
which is where things get really interesting.
Layer grouping, I don't think I've heard that before.
Instead of one layer, they stack multiple layers.
Okay.
Then these groups are repeated
Okay.
with shared parameters across the model.
So we've got these specialized experts.
Right.
And now we're grouping layers.
Yeah.
Some with shared parameters and some without.
Uh-huh.
We're adding complexity on top of complexity.
Uh,
What's the advantage of doing that?
Think of it this way.
Okay.
You're learning a complex skill like piano.
Okay.
You don't just master it all at once.
Right.
You learn individual chords,
Right.
then scales.
Mhm.
Those are like the non-shared layers within a group,
Okay.
each focused on a specific subskill.
Okay, I see where you're going with this.
Exactly.
But doesn't this create more challenges?
That's a sharp observation.
Okay.
That's where their innovation called layer norm comes in.
Layer norm.
It's all about strategically placing layer normalization
Okay.
to ensure that the residual signal
Uh-huh.
doesn't overwhelm the learning process.
So layer norm is like a pressure valve,
Exactly.
making sure the information stays balanced.
Precisely.
All this fancy architecture
Yeah.
is meaningless if it doesn't translate to performance.
You're telling me we've gone deep into the weeds here,
Yeah.
but I'm dying to know, does it actually deliver?
Yeah, do mode live up to the hype?
Well, that's where things get really interesting.
Ooh.
And that's what we'll dive into next.
Okay, so we built up this whole picture.
Yeah.
Out of Mo as this super efficient, specialized learning machine.
Yeah.
But the real question is, how does it actually perform?
Well, the researchers put it through its paces on a whole bunch of different tasks.
Okay.
They used standard language modeling benchmarks like C4, Slim Pajama, and PS2O.
Okay.
And even tested it on code generation.
And
results.
don't leave me hanging.
The results are actually pretty impressive.
Okay.
Not only did MoEUT hold its own,
Right.
but it often surpassed them.
Okay.
And here's the kicker.
Yeah.
It did all of this while using less compute power and memory.
So it's not just a theoretical improvement.
No.
It's a real-world gain in efficiency.
Absolutely.
They also compared it to another universal transformer
Right.
called SUT,
Yes.
the sparse universal transformer.
That's right.
How did it stack up against that?
That comparison is really telling.
Wow.
Mo consistently outperformed SUT across the board.
You know how we were talking about universal transformers?
Uh-huh.
Being really good at learning patterns and relationships?
Yeah, that recurrence and depth thing.
The comparison with SET really highlights that.
Absolutely.
This suggests that MoEUT's design
Right.
is ultimately more effective.
So it's not just about being clever.
Right?
It's about being clever in the right way.
Exactly.
All these tests were on tasks the Modi trained for.
Uh-huh.
What about the situations where it has to deal with something new?
Right.
How does Mo handle zero-shot scenarios?
That's one of the most exciting things about this research.
Yeah.
And Mo performed exceptionally well in these tests.
Really?
It was able to tackle new problems.
Wow.
And do so with a level of accuracy.
So it's not just a one-trick pony.
Right.
It can actually generalize its knowledge.
That has some pretty big implications.
Absolutely.
It's about unlocking new levels of capability.
This is all starting to sound a little too good to be true. There's got to be some catch, right?
Well, the researchers acknowledge optimization is needed.
Okay.
Is there a fundamental limit?
That's the big question.
They've only tested it on relatively small-scale tasks.
Right.
To really push the limits, they need larger data sets.
Exactly.
I'm curious how these experts work in practice.
Yeah.
Do they really specialize?
That's a great question, and the researchers dug into it.
All right, let's dive into that.
So it wasn't a simple case.
Yeah.
The experts showed a surprising degree of flexibility.
How so?
They didn't just stick to a single layer.
Okay.
They seemed to adapt to the needs of the model.
So they're not just static units.
That's right.
They're dynamic agents within the model,
Exactly.
jumping in where they're needed.
Right.
And this dynamic behavior, it's all data tricking.
Depending on the surrounding information.
So it's almost situational awareness.
Yeah, you could think about it that way.
That's where the power of Mo lies.
It's about a system that can orchestrate their contributions.
This has been a really fascinating deep dive.
It has.
We've gone from the high-level concepts
Right.
down to the nitty-gritty.
Yeah.
We've seen this hints at a future.
Exactly.
We could have models that bridge divides.
Yeah.
There are some challenges to overcome.
Yeah.
But the possibilities are truly exciting.
Yeah.
This feels like a real leap forward
I think so.
in our understanding of how to build intelligent systems.
I agree with you.
It's a testament for the ingenuity of these researchers.
Yeah.
They've pushed the boundaries
Yeah.
of what we thought was possible
It's really cool.
with language models.
It is.
So if you're listening to this,
Yeah,
check out the full research paper.
definitely.
We'll include a link in the show notes.
Great.
There's a lot more detail in there.
Yeah, for sure.
And as always, we'd love to hear your thoughts.
Please share them.
What implications do you see for this technology?
Yeah. What questions does this raise for you?
Keep those questions coming. Keep exploring.
And keep diving deep.
Until next time.
We hope you enjoyed our discussion today.